Hello fellow geometers. I hope everyone is doing well today. We are going to be talking about areas of regular polygons. Now before I get going, I should probably remind you that you're to show the sub your notes, and I've filled out all the notes, and so if your paper doesn't look somewhat like mine, you're probably not going to get full credit for today. So make sure that you're filling out your notes here as we go along, and hopefully this all makes sense to you. Before we get started, I want to review a little bit of what we've talked about earlier on this year, and the fact that we have covered regular polygons, but we haven't covered the area of regular polygons or how to get them. So what is a regular polygon? A regular polygon has all sides and angles are congruent. Okay, all the sides and all the angles have to be the exact same measure. All right. So, taking a look at some of the terminology that you're going to have to know for this section, the center of a regular polygon is the point that's equidistant from all the vertices. So, I would write this kind of small, but point that is equidistant. Now again, equidistant means equal distance from all the vertices, from all points. So equidistant from all vertices. Okay, so over here on your picture there, let's just go ahead and label it. This point right here is going to be point C for the center. Okay, and if you're a visual person, you can put point C. Okay. A radius. Now you may be thinking to yourself, a radius? What are you talking about, Mr. Couples? A radius belongs in a circle, not in a polygon. However, when we talk about regular polygons, there can be a radius present because, move this out here, make a little mark. The polygons that we're going to be working with, nah, that doesn't work out like I wanted it to. Maybe it's supposed to be a little bit longer, are going to be inscribed in the circle. Okay? Now obviously, maybe I wasn't dead on the center, but if you remember inscribed versus circumscribed, inscribed means when all the vertices are on the circle. Okay? So inscribed means something's inside, circumscribed means something's on the outside. All right, and so as a result, if my polygon would have been regular, I guess I didn't copy it over correctly, but each of these vertices would have to be on the circle. And so that's what I really want you to see as we look at this, is that this circle is circumscribed about the polygon. Now how does that make one of these a radius? Well, the distance from the center to any point on the circle would then be a radius, correct? And so as a result, when I talk about a radius with respect to regular polygons, what I'm referring to is basically the distance from the center to a vertex. So let's write that down. The distance from the center to a vertex. Okay? And so this could be considered a radius. This could be considered a radius. In fact, any of these could be considered a radius, depending on how you want to look at it. So they are all of equal length because that distance will always be the same. So I'll make a little note here that the radius length is going to be AC, or you could say BC, it doesn't matter, those are all radii. Okay? The apothem. Now, I'll be shocked if you guys have used the term apothem before, but the apothem is the distance from the center perpendicular to a side. So the distance from the center of the circle, not circle, center of polygon, comma, perpendicular to a side. Okay? All right, and what I'm referring to with that, to give you a visual aid of this, would be this. If I drop this line down perpendicular to this side, let's say at the point D, CD would then be considered the apothem length. Now, many times, and I'll refer to this as we continue on, the apothem is actually the height of the triangle. All right, so make a little note of that, and you can see that here, that we have a triangle here, and the apothem is actually the height of that triangle. And so as an example, we'll say CD is the apothem that's shown in the picture there. Central angle, another key term that we're going to have to know, is an angle formed by two consecutive radii. Okay, and so an example of this you could use for the central angle, angle BCA is a good example of a central angle. Now, before we move on from here, the most important formula, I'm going to give you 3 formulas today, but the most important one is going to be this one right here, and that's this. I'd like you to go ahead and show that each of the sides of this polygon have to be the exact same length if it's going to be regular. Okay? And then I want you to go ahead and draw in all of the other radii within this polygon. Okay? Now my question is going to be this. How can we figure out the measure of one of these central angles? Now hopefully you already understand, or you can visually see, that each of these central angles have to be the exact same measurement. And if you haven't already shown that on your paper there, go ahead and put it down for me. And with that understanding, we know that if we travel from this point here and go all the way around right back to that same point, we've traveled 360 degrees. If in this case there are 6 equal sections along that little travel that we just did, that little around the world that we went, you're going to take 360 and divide it by the number of sides or the number of angles. It's the exact same thing. And so down here, if you want to read the little explanation there, I give you the formula. 360 divided by the number of sides will always give you that central angle measure. Now, how does that play out within these regular polygons that we're going to be looking at? Well, if you take a look at number 5 here, all right, angle 1 is a central angle, and that's where you want to start. Angle 2 is not a central angle. The reason being, angle 1 connects 2 consecutive radii. I think you can see that from the previous example I gave you. Angle 2 does not. It actually is broken up with the apothem right here. So we have the apothem with the radius. And so we always start with the central angle. So angle 1, and I'm going to do 360 divided by the number of sides, which would be 5, which is going to be 72 degrees. Okay? Now that's key because that's going to help me figure out all the other angle measurements within this diagram. From there, I hope you recognize if we have an isosceles triangle here, which we do, and the vertex angle is 72 degrees, each of these angles will be congruent to each other because this line drop perpendicular to base breaks the 2 triangles up into congruent triangles. So as a result, angle 2 is 72 divided by 2, which is 36 degrees. Okay? And then from there, I hope you can see that this triangle right here, we know this angle, we know this angle, and we can figure out angle 3 by taking 180 minus the 2 angles that are present. All right, and so as a result, you can figure out all those. So I'd like you to take a moment and see if you can do number 6, 7, and 8. See if you can figure those out. I will tell you this, you always want to start with the central angle. So in number 6, I gave you the hint. Angle 4 is the central angle. So go ahead from there and see if you can figure out those angle measurements. Pause your video here because I'm going to go on in just a second and start talking about how to find those angle measurements. See if you can do that on your own. All right, so for number 6, I'm going to start with angle 4 again because it's the central angle, and you always start with the central angle. 360 divided by 4 gives you 90 degrees. So we know that this is a right angle here, as is this one, and this one that connects those two. Now remember what we said before, this angle is broken up into 2 congruent angles. So angle 1 is going to be half as large. Okay. Down here I hope we can see that angle 3 and the other angle are going to be supplementary because they form a straight line. So angle 3 is going to be 90 degrees as well. And then angle 2, we have 45 here, 90 here. Now we've done enough of these triangles. It's a 45, 45, 90 triangle. Okay. All right. Looking at number 7. Again, I want to identify which angle is the central angle first. So I hope that you identified 7 as being my central angle. Here's a radius and here's a radius. So angle 7 is the central angle. 360 divided by the number of sides, which would be 3, is 120 degrees. So this is 120, this is 120, and this is 120. Likewise, these two angles are going to be the same. So angle 5 is half as much. So 120 divided by 2. And then angle 6, if this is 60 and this is 90, obviously because they make a straight line, and then from there we've done plenty of those triangles. It's a 30, 60, 90 triangle. Okay. Number 8. 8 is the central angle. We're kind of lucky. 7 was the central angle for number 7. Number 8 was the central angle. How convenient. All right, so angle 8 is going to be 360 divided by how many sides do we have? 2, 4, 6 sides. So it's going to be 60 degrees. Okay. Angle 9, this is 60 degrees right here. Okay. So as a result, this angle and this angle have to be the same. Angle 9 is going to be 30 degrees. Half as much. I'm taking the 60 and dividing it by 2. Okay. And then angle 10, well, if this is 30 degrees and this is 90, again, because they form a straight line, 90, 90 make 180, this angle has to be a 60 degree angle. Again, it's a 30, 60, 90 triangle. Okay. So again, I hope that was basic. It wasn't too difficult. Finding the angle that measures out always starts with the central angle measurement. Now, from there, if you take a look at the next section, let's see here. It says here, in previous sections we've talked about how to find the area of triangles. Use that understanding to determine the area of the following polygons. So I'm actually going to give you 2 different formulas that you're going to follow tonight as you work through the next couple of sections. And so the first formula I think is one that you're going to remember. Again, this is for the area of a regular polygon. You're going to remember, hopefully, in the next year and the year after when you start taking your ACT, because it's a very basic formula. And here's what it is. If I can find the area of one triangle, that's supposed to be 1, sorry, 1 triangle, and multiply that by the number of triangles within the figure, I can figure out the area of that regular polygon. So what I mean by that is this. If I go ahead and take all of these radii and connect them, take a moment and go and do that. If you have to pause your computer, go ahead and do that. Okay? What we see here is that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different triangles, all with the same area as this one right here. Okay? And so if I take my formula, 1/2 the base of the triangle, which is 8, times the height of the triangle, which is 12.3, that's the area of one triangle, and there are 10 triangles in that picture. Now, I will want you to know that the number of triangles is equal to the number of sides of the polygon, okay? And so this is a decagon, has 10 sides, well, and it's got 10 triangles within it as well. The other formula that you could use, and it doesn't matter to me which one you want to use. In fact, I believe on the OGT, the area formula for a regular polygon is the one I'm going to show you right here. It's a little more technical in its terminology, but it's the exact same thing, and it's this: 1/2 the apothem, and we all know what that is now, times the perimeter. Okay? And so as we look at this, the apothem is 12.3. I'm going to plug this in, 1/2. 12.3 is the apothem. And the perimeter for a regular polygon, because all of these sides are the same length, is just going to be a side, I'll make a little note of this, side times number of sides. Okay? And so as a result, if you have a length of 8 and there are 10 sides, since they're all the same length, we can just do 8 times 10. Okay? Now, to make sure we understand that both of these formulas are the exact same, what I'm going to do, let's see here, 1/2 matches up, 12.3 matches up, 8 matches up, and 10 matches up. So we see that we're going to get the exact same answer for both of these formulas. So in the end, if you calculate out in your calculator, you should get 492 square inches. Okay? And so that's how we're going to figure out the area of these regular polygons coming up to today and tomorrow as we work on these. So again, pause your computer for a couple of seconds here. See if you can figure out the area for number 10. Okay, so what I did while I paused right there, I went ahead and drew in all the triangles there, and I labeled them. There are 11 triangles here as we work through that. So hopefully you've already done your calculations. If I was to do the first formula that I gave you, the area of one triangle times number of triangles, it would be something like this: 1/2 times the base. Now the base, 3.2, is over here as well, so 3.2 times the height, which is going to be 5.5, times the number of triangles, which would be 11. If I was to use the formula that's found in your textbook and on some formula sheets, it's going to be 1/2 the apothem times the perimeter, which in this case would be 3.2 times 11. Okay, both of these will give you the exact same answer. And if you work that out correctly, hopefully you got 96.8 square inches. Okay, 96.8. All right, now, there is a third component to what's going on today. So what have we covered so far today? We've done some terminology. We've identified how to find angles within regular polygons. We've also figured out the formula to figure out the area of a regular polygon. And now we're going to take it one step further and introduce or include those very fun triangles, the 30, 60, 90 triangles, and the 45, 45, 90 triangles. So how's this all going to work out? Well, here's what we have. In number 11, I want to make sure that we understand, first of all, that's a crazy looking 5, but this is 5 radical 2 centimeters. That's the radius of the figure. Okay? I want to keep emphasizing the terminology that you need to know for this. Now from there, the first thing you will always do is find your central angle. Always find your central angle first. Well, if I do that, 360 divided by 4 is going to be 90 degrees. You can go back to the front side, but I want to re-emphasize or solidify that formula in your mind. 360 divided by the number of sides. So if I do that, I'm going to go ahead and draw in all this so that we can see all of those 90-degree angles here, 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 and here. Okay? Now, what I'm going to do from there is drop a line down perpendicular to the base. I in some way have to find the height of the triangle or the apothem length in order to do either of my area formulas within this section. And so, as a result, we see that we have half of 90 And now we have a 45, 45, 90 triangle. Oh, that's good. It's one of the triangles that we want to work with. Now, I'm going to put up here the 45, 45, 90 triangle rule that we've been working with. Okay? And so if the hypotenuse of my 45, 45, 90 triangle is 5 radical 2, hopefully we can see that both of the leg lengths are going to be 5. Now, if you need to use your formula, go ahead and use your formula. Hypotenuse equals leg times radical 2. But I think this one's easy enough to see that. Now, I'm going to go ahead and figure out this length as well. This is 5 and this is 5 also. And so the formulas, I'm just going to use for this one 1/2 AP, 1/2 apothem times perimeter. So the apothem length is 5. The perimeter, I'll go ahead and say, is going to be 10 times 4. And if we work this out, now, you can use that formula. There are shortcuts in anything that we teach in math. There are definitely shortcuts. This is definitely one of them. I can work all this out, and I already know the answer just by looking at this right here. If this is a regular polygon, this not only is a quadrilateral, regular quadrilateral, it's also a square. So you could also say that this is 10 squared, which is 100. Now, if we work this out, 10 times 4 is 40. Half of 40 is 20. 20 times 5 is 100. So either way, you're going to get the exact same answer. And I don't want to stifle your creativity in how you want to do it. So either way you do it is fine with me. Okay? So, very good. That's how you do the first one there. The next one, if we look at that one, let's see here. Note, 4 feet is not the height. Not the height, not half the height. A lot of people want to say, okay, if this is 4, then this is 8, and I can figure things out from there. Don't do that, okay? It's a regular polygon. The apothem is not half the height. And so what I'm going to do from here, I would go ahead and draw in all your radii, okay? And again, the first thing we did on the previous problem was find the central angle. I'm going to do that again. Central angle is going to be 360 divided by 3, which is 120. All right? Now, 120, 120, and 120. Well, these two angles are the same, so this is 60 and 30. Okay? Now, I probably should have said this a moment ago. Feel free to pause the video and try to work it out on your own, because this is really how you learn what's going on, and then compare back to the video to see if you did it correctly. Moving on, reminding you of our 30, 60, 90 triangle rules. If this is 60 and this is 30, we know this is the shorter leg, that's x. The hypotenuse is 2x, and the longer leg is x radical 3. All right, so if the shorter leg is 4, what does the longer leg have to be? It has to be 4 radical 3. Okay. If I double that length, I get 8 radical 3. So in order to figure out the area of this one, I'll refer back to the other formula, not 1/2 AP, but the area of one triangle times number of triangles. That would be the one triangle, 1/2, the base, times the height, and the number of triangles I have here, 1, 2, and 3. If we work that out, just reminding you, we can multiply all the like terms here together. So 8 times 4 is 32. 32 divided by 2 is 16. 16 times 3 is 48. So the answer to this one would be 48 radical 3 square feet. Okay? So by now you've seen 2 examples, 2 different problems. Start the same way. Find your central angle. Figure out your side lengths and your apothem length, and then go from there. And so with that being said, take a moment, pause your video, see if you can figure out how to do the last problem on your paper. Okay. Well, I don't know how far you got, but I hope that you did your central angle first. 360 divided by the number of sides. How many do I have here? 2, 4, 6. Okay, 6. What is a 6-sided polygon called? Hexagon. Good, for all those you knew that. Okay, 60 degrees there. From there, let's see here, we have a 60-degree central angle. What I would do, again, I've told you guys this before, I'm a visual person, so I'm going to go ahead and divide that up into those 6 triangles there. Now I understand that this angle right here is 60 degrees, but when I drop that line down perpendicular to the base, it not only divides that base into 2 parts, half of 8 radical 3 is 4 radical 3, it also divides this vertex angle into 2 parts, thus giving me a 30, 60, 90 triangle. Now, if I rotate that 30, 60, 90 triangle, let's see here, this is 30, 60, this is my shorter leg, this is my hypotenuse, this is my longer leg, okay? And so what I recognize here is this, that if I take my shorter leg and multiply it by radical 3, I get this length. Now this may be one where you want to use your formula. It's the exact same thing. Formula or diagram, it's the same thing. It just depends on your preference. So my shorter side is 4 radical 3. I'm going to plug that in. This radical 3 is going to come straight down. Not going to change for right now. The longer leg is my apothem, so I'll go ahead and label this A for my apothem length. Now, multiplying those two together, hopefully we recognize by now that when you multiply 2 radicals of the same base, it just becomes that number. So it's going to be 4 times 3, which is a length of 12. Okay? So for this one, I'll do the 1/2 apothem times perimeter. The apothem we found to be 12. The perimeter is going to be the length of one side times the number of sides. Okay? And so if I take half of 12, that's 6. 6 times 6 is 36. 36 times 8 is 288. And the radical 3 has nothing else to multiply with. And there's the area of the last one. Okay? So I realized that was kind of a long video there. I wanted to make sure that we got all the components to it. Hopefully it was clear. I'd like you to go ahead and show the sub your notes now, and then you can begin starting your homework for tonight. You don't have very many problems, just a couple, because I know it will take some time. Again, thank you for your attentiveness, and I look forward to seeing you guys tomorrow. Good night.